Welcome to this problem-solving session. Today, we'll tackle an exciting challenge, finding the length of the longest substring with at most k distinct characters. This problem tests your understanding of sliding window techniques and efficient string manipulation. Let's dive in. In this problem, we are tasked with finding the length of the longest substring of a given string S that contains at most k distinct characters. The input consists of a string S, which can include both lowercase and uppercase English letters, and an integer k, where k represents the maximum number of distinct characters allowed in the substring. If k is 0, the result will always be 0 because no substring can have 0 distinct characters. The output of this problem is a single integer, which represents the length of the desired substring. For example, if S is a CBA and k is 2, we need to find the longest substring of S that includes at most 2 distinct characters. For the input S equals a CBA and k equals 2, the output is 3. This is because the longest substring with at most 2 distinct characters is ECE, which has a length of 3. Another example is when S equals AA and k equals 1. Here, the output is 2, as the substring AA contains only one distinct character and is the longest possible substring meeting the condition. These examples demonstrate how the value of k directly impacts the allowable characters in the substring and, consequently, the length of the result. Now, consider the input S equals 8 and k equals 3. The output in this case is 6 because the entire string 8 contains exactly 3 distinct characters, which is equal to k. Therefore, the length of the longest substring is the same as the length of the string, which is 6. On the other hand, if the input is S equals 8 and k equals 2, the result is different. Here, the output is 4, as the longest substring with at most 2 distinct characters can be either AB or BBCC, both of which have a length of 4. Now, let's look at one more example. If the input is S equals ABC and k equals 0, the output is 0. This is because when k is 0, no substring can have any distinct characters, resulting in an empty substring and a length of 0. These examples illustrate how the problem handles different values of k and how the constraints on distinct characters determine the maximum length of the substring. Finally, let's consider the constraints in some edge cases. The constraints specify that k must be between 0 and the length of the string, and the length of S can be up to 10 to the power of 4. The string S consists only of lowercase and uppercase English letters. For edge cases, if the string S is empty, the output is always 0. Similarly, if k is 0, the output is also 0 regardless of the string. If all characters in S are distinct, the maximum substring length will depend on k. For example, in ABCDE, if k is smaller than the length of the string, the result will be limited by k. Conversely, if k is greater than or equal to the length of the string, the entire string becomes the longest substring. These edge cases are important to keep in mind while solving the problem. To solve the problem of finding the longest substring with at most k distinct characters, we can evaluate several approaches, each with its own strengths and limitations. The first method to consider is the brute force approach. The intuition behind this is straightforward: generate all possible substrings of the given input string and check each one to see if it satisfies the condition of having at most k distinct characters. If it does, we track its length and update the maximum length found so far. To implement this, we would use nested loops to iterate through all substrings, and for each substring, we could use a set or dictionary to count the distinct characters. However, the downside here lies in its inefficiency. Generating all substrings takes quadratic time, and counting distinct characters for each substring requires linear time. This results in an overall time complexity of O(n cubed, which becomes impractical for larger strings. While easy to implement and understand, this approach is computationally expensive and unsuitable for competitive programming or real-world applications where performance matters. A much more efficient solution involves the sliding window technique combined with a hash map. This approach builds on the idea of maintaining a dynamic window that satisfies the condition of having at most k distinct characters. Instead of generating all substrings, we dynamically adjust the window size as we traverse the string. Here's how it works: we use 2 pointers, left and right, to denote the boundaries of the window. As we expand the window by moving the right pointer, we add the character at the current position to a hash map, which tracks the frequency of characters in the window. If the number of distinct characters in the hash map exceeds k, we shrink the window by moving the left pointer until the condition is met again. Throughout this process, we keep track of the maximum window size that satisfies the condition. This method is highly efficient, as both pointers traverse the string at most once, resulting in a linear time complexity of O(n). The hash map operations, such as adding or removing characters, are also efficient, with an average time complexity of O(1). While this approach requires some additional space to store the hash map, the space complexity is proportional to k, which is manageable. This makes the sliding window method both practical and scalable for a wide variety of input sizes. Among the approaches discussed, the sliding window with hash map is the clear choice for this problem, as it offers the best balance between efficiency and generality. This method operates in linear time, O(n), and works seamlessly for any input string, regardless of its size or the character set it contains. The key insight here is recognizing that we don't need to generate all substrings explicitly. By maintaining a sliding window, we can efficiently explore all valid substrings in a single pass. The hash map is particularly valuable because it allows us to dynamically track the frequency of characters and adjust the window size as needed, ensuring we always meet the condition of having at most k distinct characters. While the hash map does introduce some additional space usage, this is a reasonable trade-off given the significant performance gains. In scenarios where the character set is constrained, we could consider using a fixed-size array as an alternative, but this optimization is often unnecessary. Overall, the sliding window with hash map is the most practical and scalable solution, making it the optimal choice for implementation in this problem. To tackle the problem, we need to find the length of the longest substring in a given string S that contains at most k distinct characters. The most efficient way to solve this is by using the sliding window technique, which is ideal for problems involving contiguous subarrays or substrings. Here's how the algorithm works step by step. First, we initialize three key components, two pointers, start and end, both set to 0, to define the boundaries of our sliding window, a dictionary, char_count, to keep track of the frequency of characters within the window, and a variable, max_length, to store the length of the longest valid substring found so far. These provide the foundation for dynamically adjusting our window as we process the string. Next, we expand the window by moving the end pointer through the string. For each character s end, we add it to the char_count dictionary and update its frequency. This step ensures that our dictionary always reflects the characters currently in the window. Now, we need to check if the number of distinct characters in the window has exceeded k. The size of the char_count dictionary tells us how many unique characters are in our window. If this size is greater than k, the window becomes invalid, and we need to shrink it. To do this, we increment the start pointer, reducing the window size. For every move of start, we decrease the frequency of start in the dictionary. If the frequency of a character drops to 0, we remove it from the dictionary entirely, which reduces the number of distinct characters. We continue shrinking the window until it meets the condition of containing at most k distinct characters. Once the window is valid, we calculate its length using the formula end start plus 1. This gives us the size of the current substring. We then update max_length to store the maximum value between its current value and the length of this valid window. This ensures that max_length always reflects the longest valid substring encountered so far. We repeat this process, moving the end pointer further through the string, expanding the window, and adjusting it as necessary. When all characters of the string have been processed, we return the value of max_length. This value represents the length of the longest substring that contains at most k distinct characters. The key insights here are the efficiency of the sliding window approach, which avoids redundant computations, and the use of a hash map to manage character frequencies dynamically. Additionally, handling edge cases, like when k equals 0 or when the string is empty, ensures the algorithm is robust. The algorithm relies on specific data structures to achieve its efficiency. A hash map, or dictionary, is used to track the frequency of characters in the current window. This structure allows for constant time updates and checks, which are vital for maintaining valid windows. The two pointers, start and end, enable dynamic adjustment of the window boundaries as we process the string. In terms of complexity, the time complexity is O(n), where n is the length of the string. Each character is added to and removed from the window at most once, ensuring linear time processing. The space complexity is O(k), where k is the maximum number of distinct characters allowed. This reflects the peak size of the char_count dictionary, which never exceeds k entries. Together, these characteristics make the algorithm both time-efficient and memory-efficient for solving the problem. The code solves the problem of finding the longest substring with at most k distinct characters using the sliding window technique. The function length of longest substring k_distinct takes a string s and an integer k as input. If k is 0 or the string is empty, it returns 0 immediately since no valid substrings can exist. A dictionary char_count is used to keep track of the frequency of characters within the current sliding window. The left pointer initializes the start of the window, while right iterates through the string. As the right pointer moves, the count of the character at s, right, is incremented in char_count. Whenever the number of distinct characters in char_count exceeds k, the while loop is triggered to shrink the window from the left side. This is done by decrementing the count of the character at s, left. If the count of a character becomes 0, it is removed from char_count to maintain only distinct characters in the window. The left pointer is then incremented to reduce the window size. At every step, the maximum length of the substring is updated by comparing the current window size, right left plus 1, with the existing max_length. This ensures that the longest valid substring is tracked throughout the process. Finally, the function returns the value of max_length, which represents the length of the longest substring with at most k distinct characters. This solution is efficient, with a time complexity of O(n), as each character is processed at most twice, once by the right pointer and once by the left pointer. The space complexity is O(k), due to the storage of character frequencies in the dictionary. Here, we start by defining the function length of longest substring k_distinct that takes a string s and an integer k as input. First, we handle edge cases. If k is 0, or the string s is null or empty, we simply return 0 since it's not possible to have any valid substring. Next, we initialize a hash map called charCount to store the frequency of characters within the current sliding window. We also set up two pointers, left, which represents the start of the sliding window, and right, which will iterate through the string. Additionally, we define max length to track the length of the longest valid substring we find. The for loop then iterates through each character in the string using the right pointer. For every character, we add it to the charCount map, updating its frequency with charCount.getOrDefault. If adding this character causes the number of distinct characters in the map to exceed k, we enter a while loop to shrink the window. Inside this loop, the character at the left pointer has its frequency decrement. If its frequency becomes 0, we remove it from the map, and we move the left pointer one step to the right. Once the number of distinct characters in the map is within the limit of k, we calculate the length of the current window using right left plus 1 and update max length if this window is the largest we've encountered so far. The for loop continues to expand the window and adjust the map as needed until we've processed the entire string. Finally, after the loop completes, we return max length, which holds the length of the longest substring containing at most k distinct characters. This implementation efficiently handles the sliding window with the help of the hash map, ensuring we maintain a time complexity of O(n). To solve this problem, we are given the string is cba and the value k equals 2, which means we need to find the longest substring that contains at most two distinct characters. We start by initializing an empty dictionary called char_count to track the frequency of characters in the current window. Additionally, we set left to 0 to represent the start of our sliding window and max_length to 0 to keep track of the maximum substring length we've found so far. Next, we begin iterating over the string using a right pointer. At position 0, the character is e. We add e to the dictionary, making char_count equal to e1. Since the number of distinct characters is 1, which is less than or equal to k, we calculate the current substring length as right left plus 1, which is 1. We update max_length to 1. Moving to the next position, the right pointer is now at 1, and the character is c. We add c to the dictionary, resulting in char_count being e1 c1. Again, the number of distinct characters is 2, which is within the limit, so we update max_length to 2. At position 2, the character is E again, so we increment its count in the dictionary, making char_count E2 C1. The number of distinct characters remains 2, so we calculate the current substring length as 3 and update max_length to 3. Now, when the right pointer moves to position 3, the character is B. We add B to the dictionary, resulting in char_count being E2 C1 B1. The number of distinct characters has now increased to 3, which exceeds K. To fix this, we need to shrink the window by incrementing the left pointer. First, we decrement the count of E in the dictionary, making it E1 C1 B1. Since E still has a non-zero count, we decrement it again, removing E entirely, so char_count becomes C1 B1. We then update left to 2. At position 4, the character is A. Adding it to the dictionary results in char_count being C1 B1 of 1. The number of distinct characters is once again 3, so we shrink the window by decrementing the count of C, removing it from the dictionary entirely. This leaves char_count as B1 of 1. We update left to 3. At the end of the iteration, the maximum substring length that satisfies the condition is 3. In this example, we are given the string AA and K equals 1, meaning we need the longest substring with at most one distinct character. We begin by initializing char_count as an empty dictionary, left as 0, and max_length as 0. At position 0, the character is A. We add it to the dictionary, resulting in char_count being A1. Since the number of distinct characters is 1, which is within the limit, we calculate the current substring length as 1 and update max_length to 1. At position 1, the character is again A. We increment its count in the dictionary, making char_count A2. The number of distinct characters remains 1, so we calculate the current substring length as 2 and update max_length to 2. Since there are no more characters to process, the final maximum length of the substring is 2. Now, let's analyze the example where the input string is ABCDE and K equals 3. We start by initializing an empty dictionary char_count, setting left to 0, and max_length to 0. At position 0, the character is A. We add it to the dictionary, making char_count equal to A1. Since the number of distinct characters is 1, which is within the limit, we calculate the current substring length as 1 and update max_length to 1. At position 1, the character is B. Adding B to the dictionary results in char_count being A1 B1. The number of distinct characters is now 2, so we calculate the substring length as 2 and update max_length to 2. At position 2, the character is C. Adding C to the dictionary results in char_count being A1 B1 C1. The number of distinct characters is 3, which is exactly equal to K, so we calculate the substring length as 3 and update max_length to 3. When the right pointer moves to position 3, the character is D. Adding D to the dictionary makes char_count A1 B1 C1 D1. The number of distinct characters is now 4, which is greater than K, so we shrink the window by decrementing the count of A. Since A now has a count of 0, we remove it from the dictionary, leaving char_count as B1 C1 D1. We then update left to 1. At position 4, the character is E. Adding E to the dictionary results in char_count being B1 C1 D1 E1. Again, the number of distinct characters exceeds K, so we shrink the window by decrementing the count of B. Removing B from the dictionary leaves char_count as C1 D1 E1. We update left to 2. At the end of the iteration, the maximum length of a substring with at most 3 distinct characters is 3. The time complexity of this algorithm is primarily determined by its use of the sliding window technique. Here, the right pointer traverses the entire string from start to finish, making n iterations. Meanwhile, the left pointer is responsible for contracting the window when the number of distinct characters exceeds K. Although the left pointer appears to operate inside a nested loop, it only moves forward and processes each character once throughout the entire string, contributing an additional n operations. Dictionary operations, such as adding, removing, and updating entries in char_count, are constant time operations, O1, and are performed at most once per character. Therefore, the dictionary operations contribute O(n) as well. These components together result in a total time complexity of O(n). By summing up the contributions from the outer loop, the inner loop, and the dictionary operations, the overall time complexity of the algorithm is O(n). Shifting our focus to space complexity, the primary contributor is the char_count dictionary, which keeps track of the frequency of distinct characters within the current window. In the worst case, the dictionary will store up to k distinct characters, which means the space required is proportional to k and results in O(k) space complexity. Additionally, variables like left, right, max_length, and others require constant space, which is O(1). Therefore, the total space complexity of the algorithm is O(k). To highlight the efficiency of this approach, let's compare it to a brute force solution. The naive method would involve generating all possible substrings of the input string, which takes O(n²) time, and then counting the distinct characters in each substring, adding another O(n) for each substring. This results in a total time complexity of O(n³). In contrast, the optimized sliding window technique avoids redundant calculations by dynamically expanding and contracting the window as needed, achieving a time complexity of O(n). Both approaches share the same space complexity of O(k), since they both require storage proportional to the number of distinct characters. This makes the sliding window approach significantly more efficient, especially for large inputs. When analyzing the best, average, and worst cases, we find that the time complexity remains O(n) in all scenarios. In the best case, if k is greater than or equal to the number of distinct characters in the string, the while loop never executes, and the algorithm completes with just a single traversal of the string. In the average and worst cases, the while loop executes intermittently, but the left pointer still only traverses each character once, ensuring no extra overhead. Mathematically, the right pointer traverses the string once, contributing O(n), and the left pointer also traverses the string once, adding another O(n). Dictionary operations, with their O(1) time complexity, contribute O(n) for the entire string. Therefore, the total time complexity remains O(n). For space complexity, the dictionary stores at most k keys, contributing O(k), with other variables requiring O(1). Summing these, the total space complexity is O(k). In this section, we'll focus on common mistakes to avoid when solving the problem of finding the longest substring with at most k distinct characters. One frequent issue is neglecting edge cases, such as when the input string is empty or when k is 0. These scenarios should return 0 because there are no valid substrings to consider. Overlooking these cases can lead to runtime errors or incorrect outputs. Another common pitfall is mismanaging the sliding window updates. When the number of distinct characters exceeds k, it's crucial to properly remove characters from the window, ensuring that characters with 0 frequency are completely removed from the map. Failing to do so results in an incorrect window state and invalid results. Additionally, trying to solve this problem using a brute force method, where all substrings are generated and checked, is highly inefficient. This approach has a time complexity of O(n³), making it impractical for larger inputs. Lastly, it's important to distinguish between problems that require at most k distinct characters and those that require exactly k. Confusing these requirements often leads to solving a completely different problem, resulting in test case failures. Another common mistake is the incorrect usage of hash maps or dictionaries. For instance, some forget to decrement character counts or remove keys entirely when their value reaches 0. This can lead to incorrect calculations of the distinct character count or even memory issues. On the positive side, mastering the sliding window technique is essential for problems involving substrings or subarrays with constraints. It's an efficient and versatile approach that works well for this problem. Additionally, hash maps are incredibly useful for maintaining character frequencies, allowing you to efficiently add and remove characters while tracking the distinct count. Understanding the trade-offs between approaches is also important. While brute force is inefficient, recognizing why it doesn't work helps you appreciate the optimality of the sliding window method, which operates in O(n) time. During interviews, it's crucial to clearly communicate your thought process. Explain how you manage the window, update the hash map, and decide when to expand or shrink the window. This demonstrates a structured and logical approach to problem solving. Finally, always test your solution against edge cases, such as empty strings, single character strings, or extreme values of k. This ensures your code handles all scenarios correctly. There are several related problems that build on similar concepts, and exploring these can deepen your understanding of the sliding window technique. For example, LeetCode problem 159 asks for the longest substring with at most 2 distinct characters, which is a specific case of this problem. Problem 340, which we're discussing here, focuses on at most k distinct characters. Another variation is problem 3, where the goal is to find the longest substring without any repeating characters. Finally, problem 992 deals with subarrays containing exactly k different integers, which introduces a slight variation in constraints. Exploring these problems helps you recognize patterns and adapt solutions to different scenarios. When considering alternative approaches, it's essential to weigh the trade-offs. For example, while brute force may seem straightforward, its inefficiency makes it unsuitable for competitive programming. On the other hand, the sliding window method is both optimal and versatile, making it the preferred choice for these types of problems. Let's compare different approaches to solving this problem. The brute force approach involves generating all possible substrings and checking the count of distinct characters in each. While simple to implement, this method has a time complexity of n cubed, and is impractical for larger inputs. On the other hand, the sliding window approach with a hash map is highly efficient, with a time complexity of n. This method optimally expands and contracts the window while maintaining the count of distinct characters. However, it requires careful implementation to ensure that the hash map is updated correctly. Another alternative is using 2 pointers combined with a sorted data structure, such as a balanced tree or a sorted map. This approach has a time complexity of n log n, as maintaining the sorted order adds additional overhead. While more complex, it can be useful for variations of the problem that involve additional constraints, such as requiring substrings to be processed in lexicographical order. Choosing the right approach depends on the specific problem requirements and constraints, but for this problem, the sliding window method remains the most practical and efficient solution. Great job! Today, we mastered an efficient sliding window technique to solve the problem of finding the longest substring with at most k distinct characters. Remember, this approach is versatile and can be adapted to many similar problems. Thanks for joining, and don't forget to practice and stay consistent. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!